I want to thank the organizers of this webinar series. I'm very honored to participate, and I want to thank Oreille particularly for inviting me. So, so yes, as Oreille said, this is sort of work in progress, and from this zinc synthesis group that we put together. And so this is eventually we're going to have a manuscript. So as we have been talking about, climate change has an effect on rivers, on the temperature and the flow. And the latest has been, as of last month, on the Klamath River, for example, in California, an outbreak of a parasite because of warm temperatures and caused fish kill of Chinook salmon. Chinook salmon in this basin, the Klamath, is of cultural significance for the Yurok tribe. And another example was in 2018 in the Rhine River, where there was a fish kill on grayling. And so we see this everywhere. So compounding, climate change with changes in just population and water withdrawals, or just use of groundwater extractions, land use legacy effects from, for example, in the Pacific Northwest on logging, or in the Northern Europe. So all these things sort of exacerbate the effects of stream temperature. And the stream temperature is a very important variable for fish distribution, or just biota distribution and growth potential. Here we have sort of a watershed map where it shows the general pattern of thermal heterogeneity, where streams, the headwater streams are cooler than the main stem here at the low elevations. But even within that, there's some nested hierarchy where there are some cold patches of water within this warm section. But warm water is not always bad, particularly during the shoulder seasons, like the fall and the spring, where the growth potential for fish, particularly salmonids, can be better than in the summer when it's crunch time, because of the temperature has gotten beyond the optimal or close to lethal temperatures. So this here, this thermal heterogeneity at the smaller scales is what we sort of called as a thermal refuge. So what's a thermal refuge? And it's a place that is an area that may be either cold or warm in relation to the surrounding water. And particularly in the summer, when, for example, a fish is hanging out at a 25 Celsius area with subsurface inputs versus in the main stem where it's 27, that's what we would call the thermal refuge. An area that is colder than the surrounding area, the surrounding water. And this can be, this definition can change depending on, the management perspective. Either you can use physiological thresholds, or just degrees between the ambient temperature and that patch of water. So things get complicated because how much is enough, how big of a patch, how many patches, the special arrangement, where, when, those kind of things. And that is when we have to think about what is the knowledge required for managing these cold water refuges. On one side, we have the physical and biological, sciences, what kind of physiological thresholds do we know, the species interactions of these patches or these refuges. What is the hydrological and geomorphological template that creates these patches? What are the effects of climate change and anthropogenic disturbances on these patches? And what are the spatial and temporal skills that we need to be interested in? And then there's also the socioeconomic side of things. What's the cultural and economic significance of these areas? Are there conflict of use? And generally that is true because these are areas that have groundwater influence. And so there may be some groundwater abstraction, or there could be, just the fishing, people, they're going to be fish use in these areas. And then translating all this importance into good stewardship. How do we do that? And knowing, understanding that relationship, and then understanding the appropriate scale of the governance of these places. Um, so there are a few factors that affect or sort of delay the translation of the science into management and policy. One of them is the absence of or limited consistent terminology and metrics. People use different definitions of what a coldwater refuge is, metrics. Do we measure area or volume, things like that. And then also integrating ecological resilience principles like temporal variability, spatial heterogeneity, hydrologic connectivity. All these things can make it harder for to manage. And then also having clear policy objectives and constraints, because science informs management and policy, but policy also informs science, and so to be effective. So so the first step to be able to manage these areas is to know where the fish are, and know where these cold patches are. So have some good physical biological monitoring, and there's already in place a lot of stream temperature networks. Here I have some examples. The Northwest and in the United States, Scotland River Temperature Monitoring Network. In France has some networks. This is in Canada. So, but unfortunately, they're mostly focused on minimum and maximum temperatures and mean conditions. So they're not focusing on that heterogeneity that we're interested. Also, it may be more costly, monitoring where the fish are located, whether they're using it. There are other factors that affect the use of thermal refuges, like dissolvable oxygen, or salinity, those kind of things. So once we have that information, or where these refuges are located, then we can integrate the biological information with some models like bioenergetics, or we can also include, merge the groundwater and the surface water temperature models using either statistical models or mechanistic models. And so we get a better picture for managing restoration efforts, or climate change effects, water withdrawals, all sorts of things. So what to do? What to do next? How do we implement this specific policies and management related to cold water refuges? And what are the impediments preventing such implementation? So this graph sort of shows how, and this is from, sort of American perspective. We have here some parts of the Clean Water Act. So, but I imagine in any region, there are some policies related to water quality policy. And then on the other side, species conservation policies. And so generally, these policies are either from reach scale to watershed scale. And so we have riparian management, wetland, groundwater, thermal discharge guidance. And so at the moment, for example, in the US, some of these things don't really deal with cold water refuges. This is just water quality standards in the Pacific Northwest, particularly in Oregon, where there's policies explicitly interested in cold water refuges. But there's a lot of possibilities and potential links where if we explicitly call out cold water refuges, we can link this to the species conservation policies, and having in mind those resiliency concepts, of connectivity, spatial temporal heterogeneity, what's sufficient, what's persistent. And this is something that the EPA has been working on the Columbia River Basin. So I'm gonna talk about more about management perspective here, I have a case study, the Oreille River. This is one of the largest tributaries of the Columbia, and is the Kalispel tribe has its reservation in the watershed, and they're very interested in bull trout because it's of cultural significance and the West Slope cod trout. Both the species have declined, particularly bull trout. Their passage was basically cut off because of the dams that were put in place. And so the tribe has been working really hard to get the passage through the dams. But unfortunately, water temperatures have increased. And so water temperature normally exceeds 20 degrees in the summer, which are too warm for bull trout, which is sort of a picky species. So here we have, and I'm not going to go too much into detail this slide because it's pretty rich in data. This comes from this paper that we published in 2020. This is sort of a run-of-the-river reservoir, and it's bounded by, our study site was bounded by Albany Falls Dam, this is the one that has problems with the passage of the fish, and then Box Canyon Dam. Box Canyon Dam is mostly for hydroelectric power, and it produces a lot of electricity for the city of Seattle. Here we have the distance upstream, 144 kilometer here is where the Albany Falls Dam is, and then 55 around, that's where Box Canyon Dam is. So it's a pretty warm river, and also, with the flow regime altered and thermal regime, you still see some heterogeneity, and there's some peaks and valleys that I would like to point out. For example, here, river kilometer 80 is the coolest spot in the river, on general terms, the surface and the bottom, and this is due to a tributary confluence. And here we have the largest sort of discrepancy between the surface and the bottom loggers. Is a pretty wide section of the river, and there's a lot of submerged aquatic vegetation, which sort of steepens that gradient of temperature and use of oxygen. And then we have areas here with groundwater inputs that sort of cools it down. And here, I think these warm temperatures here are from the epilignetic releases from the Albany Falls Dam. So, and I should have said that the gray and the black dots and the dotted line is from the thermal infrared data that was collected in 2001. And this the cyan and purple are the in-stream loggers that were put in place in 2017. So the major source of thermal heterogeneity here in this river, because of the thermal regime that has been altered, is really the tributary confluences. And then here we see that there are a number of tributaries that are completely stratified, like this one right here, C4, and it remains pretty cold during our whole time of sampling. On the bottom, and then on the surface, it was fairly warm. And then we have, things that are sort of in flux, and then there are other things that are pretty well mixed, like this tributary here, 616, which is this example. But when the reservoir, the water is high, then it becomes warmer because of that backwater effect. And so, this was a good candidate for restoration or enhancement, as we're referring to. And so this is a thermal imagery, and you see sort of here at the confluence, it's cooler. And this is a shot of the, I'm not gonna go too much in detail, but one of the efforts is to provide some more in-stream cover, because it lacks of that, and make the stream channel here at the confluence narrower, and so the water velocity is greater and deeper, and then create a pool here at the end at the confluence. So, the fish can hang out here, avoiding predators, and create some sort of berm with some large wood, and just sort of I think basically the idea is to keep the water maybe a little longer so fish can benefit from it. There are, this is hard work because it's a regulated river. There's not many places
C'est un
where
travail assez difficile. La rivière est régulée.
And a lot of abundant submerged aquatic vegetation because of the changes in the flow regime. And so, as I alluded before, the steepens temperature and dissolved oxygen gradients. There are other places in the river where we have observed hypoxia in the night. So there's also politics of the water management. The way the river is managed, there's not really much room to be changed. The upstream is, the water is held back in the summer for recreation. It brings a lot of money to the state of Idaho, so it's another state. And then there's, on the other side, and on the other end, there's hydropower for the city of Seattle, which is also very important. So that would be difficult to change. So the broad scale thermal restoration is unlikely, something changing flows and that type of thing. So the cold water refuge augmentation and enhancement at small scales is the only or the more feasible way to go. And there's also limited community participation. The only, I think, group that is interested on this type of restoration is the tribe. But eventually I think all the stakeholders need to collaborate. So engaging that probably is an important step. And then the regulatory framework is very fragmented. There's multiple agencies with overlapping jurisdictions and goals. So that's a challenge for the tribe. So there are other case studies, I work in the Pacific Northwest. So this is where, I've been more, aware of those projects. But there's, plenty of projects here on the East Coast, Nova Scotia, and New Brunswick. And then there are some very interesting projects on the Walker River, with water transfers, aquifer rechargers, and in Idaho on the Snake River and the upper part of the Snake. And then floodplain reconnection projects in the Columbia Basin. And but there's other opportunities like dam releases on the East Coast, mitigation banking. I haven't seen examples of that. Riparian buffers. And on the European side, there's a project that I think is starting in Switzerland, where there's going to be stream network temperature monitoring that is going to include cold water refuges. And then along with that, in the southeast of France, there's also been projects identifying these cold water patches. And so I think on the management side, I don't think there's there are not many examples in Europe. So just to sort of, put it all together here, the first step is to identify these cold water refuges, monitor, model, and then recognize their importance, look at the kind of tools we already have in place, integrate those and adapt them to be able to, manage for cold water refuges. And if none are in place, the next step, which is probably harder, is to build new capacity, to be able to manage these refuges. I have 5 take-home messages. The first is that, we need to think about including these cold water refuges, explicitly in management and regulation, because that probably is the first step, recognizing their importance, identifying where they are. And then when we manage for temperature, not to focus so much on the average conditions or the maximum conditions, but look at those, that thermal heterogeneity, because even in the warmer spots, there will be some, areas where we could, have, some room to play with. And then recognize cold water refuges have multiple uses, so it's not just fish, it's, humans, groundwater abstraction, those kind of things. And then conserve the cold water refuge as a part of the aquatic ecosystem. And then last one is to build the capacity across regulatory jurisdictions so we can manage them. Again, I want to thank the whole group that participated in this effort with SYSYNC, which was the National Socio-Environmental Synthesis Center that allowed us to get together. And then just ready to take questions. Thank you.